So let's continue talking about atomic models and electrons. We left off last time with the Bohr planetary model, which solves some issues with the Rutherford model, namely, what are the boundary conditions of the atoms? Why don't the electrons collapse into the nucleus as negative charge is attracted to a positive nucleus? And the answer is orbits, really for both of them. Why don't electrons collapse into the center? Because they're moving in orbits like planets around the sun. What are the boundary conditions? Well, whatever the biggest orbit is. But there are also problems with the Bohr model. There's no immediate explanation why energy has to be quantized, meaning the orbits are fixed. There's a fair bit of experimental evidence that we'll talk about later in this class that suggests they are in fact fixed. And then you have the problem of scale. Nuclei and electrons are just not suns and planets. And so there's no actual direct evidence that perfect round orbits around the nucleus actually do in fact exist. And so we make one more kind of move in the early 20th century to what is now considered the electron cloud model or the quantum mechanical model. The quantum mechanical model says that there are not really perfect orbits that we can track. What we can tell you is where electrons are likely to be found relative to the nucleus. And so we have these kind of nebulous cloud regions that we refer to as atomic orbitals. And atomic orbitals, rather than being perfect orbits, are really just regions of space around the nucleus where there is a statistical probability of finding an electron. And that's the best we can really do. And there are really two ways to think about atomic orbitals. If electrons are not moving in perfect circular orbits, if they are in fact just moving erratically around the nucleus, but still attracted to the nucleus, if we can imagine the path that they trace out over a long period of time, that might in fact define this region of space. You can think about it like the night sky. If you look at the night sky, you see points of light, stars in distant galaxies that look like stationary objects. But it turns out if you open a shutter on a camera and do a long exposure, what you find out is those stars are actually moving over the course of the night, just like the star that's at the center of our solar system. They rise in the east, they set in the west, and they rotate around a seemingly central position in the night sky, at least in the northern hemisphere, that we tend to refer to as the North Star. But you can see from this image that over time, the motion of those stationary objects or seemingly stationary objects trace out a pattern, trace out a shape. And you can think about orbitals the same way. If we were able to do time-lapse photography on an electron and then trace its path over time, and we could map out where that electron spends 90% of its time, that region of space would be considered an orbital. The second way to think about it is to think about it as an energy field. And again, electrons are charged particles. They have certain energies, and around them are energy fields, just like there are energy fields around magnets. So there is a space around a magnet that responds to the environment in a certain way because there's a magnetic field around that magnet. And we can actually trace those magnetic field lines with a bit of powdered or iron filings around the atom, and you can actually see as those little bits of iron align themselves along those field lines. Different shaped magnets give you different field lines, much like different energy electrons are going to give you different shaped orbitals. And when you put two magnets together, those magnetic field lines distort the different arrangements of magnets and the different energy of magnets. So here we have a north to south. Here we have a north to north. That distorts the energy field in a different way. And here we have a north-south bar magnet turned perpendicular, which distorts the field in another way. Electrons, or electron orbitals, I should say, are regions of space around the nucleus that depict the particular energy of an electron at a certain point. And if you have multiple electrons in an atom, then those energy fields are going to distort to try and avoid one another because the electrons are both negative. Here are some images of some 3D modeling of different atomic orbital shapes of different energy electrons. And you don't really necessarily need to make sense of all of this right now. We're going to hit all of this stuff, but atomic orbitals essentially are just regions of space generated by a bunch of electrons trying to get as close as they can to the nucleus and as far away as they can from each other. And when you start moving down the periodic table, things that have 15, 20, 30, 50, 100 electrons, you can end up with some pretty bizarre energy fields when you have that many things vying to get close to the nucleus, but at the same time trying to stay as far away as they can from each other. And so these atomic orbitals represent the energy of electrons. The size of the orbital tells you something about, again, the energy of the electron. And the bigger the orbital, the further away from the nucleus the orbital is, the higher energy electron you have, as those orbital energies are moving up, again, the quantum ladder. And again, with the quantum ladder, the higher energy you get, the closer those energy levels get together. And so in our next video, we're going to look at some other bizarre features of electrons. And then we're going to come back to this idea of electron orbitals, and we're going to define some of these shapes and how we understand how they work.